Let's go through and think about the uncertainty principle kind of qualitatively. So the basic idea is that we have an uncertainty in position and uncertainty in momentum for a given state, and that uncertainty can never be less than h bar over 2. We can construct states where it's greater, but not less. So let's go through and think about some different states. So if I have a delta function, basically, in position, that delta x is very small. But if I say, well, what is delta momentum? I would basically say, well, what does it take in momentum space to get a delta function? And the answer is, in momentum space, you would actually need kind of all terms, basically. You would need really all momentum terms. And the more narrow this is, the higher and higher and higher momentum terms you need, corresponding to higher energies, which give you those sharper pieces. So this is very, very high. Okay, so then let's imagine, so this is basically a delta function in position. Now let's consider a plane wave. And we call it that because we think about it happening in like 2 or 3 dimensions. But what this would basically be is just one of our beautiful sine waves. What is delta x? Very large, because this is literally a wave that's just repeating over and over and over again, filling all of x. So very large. And if you wanted to say infinite, okay. But then what do we have in momentum space? Well, depending, if we call this a standing wave, we would have 2 terms in momentum, but otherwise, we basically have just one momentum term if we let it propagate to one direction, right? This is what a momentum eigenstate looks like. So this is very small. And again, if we wanted to say, well, this is really only one momentum state, we could say that this is 0, but then it literally has to fill all space and this becomes infinite. And it's actually the same situation as here, just reversed, right? This is that idea of that Fourier transform. We can go back and forth. So in this case, again, depending on exactly how you construct it, you potentially can get to 0 times infinity type terms. So we would never actually do that exactly. There would be like a small width. So then the next thing would be a Gaussian. And this is one that I did out kind of more exactly. So we have a Gaussian. What do we get for delta x? Delta x is equal to a over 2 in the case where this is e to the negative x squared over a squared. And the reason I say that is because there's different ways that you can actually define kind of the width of your Gaussian. So if this is how we're defining our Gaussian, this is what we get for delta x. What does that look like when we do the Fourier transform? We actually also get a Gaussian. And delta p is then equal to h bar over a. So with these, it's a little bit tricky because they're very idealized, and you kind of would get an undefined uncertainty principle. If we make this slightly not a delta function, then we can calculate exact values here. But one way is we can actually get Gaussians, and that then you have it exactly equal. So you can imagine a scenario where, for instance, we maybe have just 2 momentum states that we've added together, so kind of a beat scenario. And then that's something we can calculate. And in fact, then we would probably have something that is much larger than what the uncertainty principle requires. So this is our minimal uncertain state dealing with Gaussian, and it's kind of a nice example of a wave packet. Now, something to know is that in your simulations, you're not normally going to see an exact Gaussian. You're going to see something that looks, more like that. And you can kind of see that there's a Gaussian envelope. And exactly, how we think about this in terms of a Gaussian or not, there's a question of, well, how many terms have you put in here? What's the relative phase between those terms? So thinking about a Gaussian is a mathematically simpler way than thinking about a wave packet we've built out of discrete states, though oftentimes in the simulation that's what we can do. So recognize in the simulation it might look very squiggly, but the envelope is really a Gaussian.